Alright, well thank you for having me. I've just learned, in fact, that the only other time I've been here for a brown bag is for the other exceptional one where Kate invited a friend. So, but suspecting that Kate might just be inviting people that talk about things she's interested in, I've kind of moderated the content somewhat, so hopefully there's something for everyone. So I'm broadly going to be talking about how a machine can learn meaning, so why that's a problem at all, and one way you might hope to do it. And then there'll be a bit of a change of pace, and I'll be talking sort of about two different actual implementations of that idea that have come out in recent years, and sort of comparing them to historically, if it's not too strange to talk about history when it's only a few years old. But good. So first, maybe something about me. So it sounds like you got it from Kate, but I'm a machine learning consultant, and I run a machine learning seminar around the corner, which Kate participates in particular. I'm an ex-mathematician, and I co-founded Lateral. But importantly, I'm not a trained linguist. Many of you probably are, so I apologise in advance. But that's where we're at. All right, so yeah, first I want to convince you that there's actually a problem to be solved. And the first thing to realise is that machines see words just as meaningless symbols, which is a total truism when you think about it, but it's hard to actually get it into your head because we're used to knowing what words mean. But you can imagine taking your text in a language that's written in a language that you don't understand and trying to read it. That's how a machine sees language a priori. So if you take two words which for us are very similar, like ship and boat, and you compare them, or a computer compares them, it sees them as being as similar to one another as two totally unrelated words, like cat and dynamite. They are totally different ship and boat, as far as the computer is concerned. So it's really kind of autistic in its precision about language, which isn't necessarily a problem. Like it's the thing that makes keyword search work brilliantly. So if you know the title of the document you're looking for, the best thing you can do is go to a search engine and just put that title in, and you will get it straight away. Because it's not trying to sort of interpret what you might mean, it's giving you exactly what you said. So it's great for things like search. It's crap for stuff like discovery. So by discovery I mean you don't even know what you're looking for. You don't know how to formulate it. Maybe you're not even looking because you're not aware of what you don't already know about. So this is the problem that Lateral around the corner is trying to solve. We try and look at what you're working on and surface relevant material. So you can imagine you might be working in some really big company and you're writing a report on some project, and you just couldn't know that someone on the other side of the planet 10 years ago worked on something that's actually really relevant. So the idea is just to surface that by looking at what you're working on. I mean, it's the same tech for like content-based recommendation on news websites, for instance. It's exactly the same problem. So it's to help people find what they don't know is there. That's why it's important for us to understand the meaning of words. But it's not a problem for everyone. So how can we hope to teach a machine the meaning of words? Well, there is this idea which I'm told comes from linguistics, popularised by Harris in 1998, called the distributional hypothesis. And what it's saying is that it says, quite literally, words are characterised by the company that they keep. So if you want to know what a symbol means, look what other symbols appear near it. So ship and boat can be seen to be similar from this point of view because they both occur near the same sort of words. So stern and sail and sea are all equally likely to occur near boat as they are near ship. On the other hand, like words like glycerine and meow aren't likely to appear near ship or boat. So by looking at this information and measuring it, you can hopefully see that ship and boat are the same, even if you don't understand the language you're looking at. So to just sort of formalise that idea a little bit, let's imagine we're trying to understand the meaning of the word cat. Or you formalise it as a conditional probability distribution. So big word, but imagine you just read the word cat. Now go along and see what other words appear near it, and do that for a whole heap of occurrences of the word cat, see which words appear near it. And by doing that, measure the probability of seeing a word given you've seen the word cat. So imagine you just read the word cat. What's the probability of any other word appearing next to it? So you've got some fixed vocabulary, you've got words like meow, potato, parrot, spaghetti, fleas and pet. You've just read the word cat. It makes sense the word meow is more likely to occur than the word potato. This might be a bit small to read. Similarly, fleas and pet are quite high up for the word cat. Buggy's very low. Parrots has got a little bit thing because people like to write books about cats and parrots. So you've made this measurement right, you've got this probability distribution. In a sense, you're actually done. You've now just represented the word cat by a really long vector of probabilities. So for every word in the vocabulary, you've got a dimension. And in each dimension, you measure the probability of that word occurring with the word cat. So you've got a representation in the computer of the word cat. And because of what we said before about similar words occurring in similar contexts, this gives you a representation that captures meaning in a very blunt thematic sense. So there you're in a really high dimensional space. You've got as many dimensions as you've got vocabulary. You then do some magic dimension reduction. And this is compressing that information to a much lower dimensional vector space. And this bit of magic is the bit we'll get to later on when it gets a little bit more technical. But imagine you've done this in a way so that things that were close together in the high dimensional space are still close together in the low dimensional space. Well then, words that are similar are going to be close together. So imagine we did this down to two-dimensional space. We might get something like this. You probably can't read this, but these blue spots are representing words, and I've labelled them. So here's man and here's woman, here's dog and here's cat, here is king and here is queen. So similar words are close together. So man and woman are quite similar relative to words like dog and cat. King and prince, king and queen are quite similar. They're close together as well. And here we've got mouse and cheese. So if you could read the labels, another thing you'd notice is that, well, maybe just bear in mind the relationship here between man and woman and king and queen. Because the neat thing is, if you do this correctly, the displacements between two words represent the word relationships. So, what I mean by that is king is the queen as man is the woman. Just as uncle is to aunt. So the line segments, if you like, joining man to woman, it's a bit hard to see, but there it is there. Well, it's parallel to the one that joins king to queen. Right? So we haven't just got, we're not just looking at things being close together in space, but also the displacements between 2 points representing something about their word relationship. Kind of cool. So, that word displacement thing is something that got people very excited about this a few years ago. An application to, or maybe a relationship to machine translation is another thing that got people excited about it. It's in particular what got Kate talking to me in the first place. So imagine that you have one of these representations for English and another one for Spanish. Well, in an ideal world, the words in English will be in relative position similar to the words in Spanish that they translate to. So what I mean by that, this is way too small to read, but okay, here's horse and here's cow. This is on the English side here. Then on the Spanish side here in blue we have caballo and vaca. Here we've got the numbers. So, oh God, not even I can read that, but
maybe it's better if you stand here. So you have 4 on top and then 5, and then 3, right?
Your screen's gonna
oh, yeah.
save it.
Okay, great. So top left on the English side there, we've got 4 and 5. And here we've got 5. So the words stand in the same relative position to one another, right? So the idea then is you can, I mean, everyone knows how to translate the word one in English to the word one in Spanish. That's not hard at all, right? But you've got all these example translations. So you can then train a transformation that takes you from this English space to the Spanish space by using the knowledge you've already got. And then you've got some English word you don't know the Spanish translation of, well, you can just send it through that transformation and see what it's closest to in the Spanish space. I don't know if it's actually practically useful, but it's kind of cool. All right, so that's the general approach to how machines can learn meaning and why you might care about it. How do you actually do it when the rubber hits the road? How do you actually implement it? Well, in the last few years, there have been big advances in this field, and it's really turned computational linguistics on its head. So at this conference Kate and I went to last year in Portugal, there were maybe a third of the papers, more?
Yeah.
Like,
the keyword is word embedding up there. This is like the association with this, and yeah, it was at least a third, maybe up to half.
Yeah, it's
about this.
Totally disrupted this field. Before then, like, computational linguistics was predominantly human curated and rule based. And all of a sudden you're training these magic boxes that learn language from text, and it's really changed the field. So there are 2 events. The first one is the one that really brought about this revolution in my point of view, and it was called Word to Vec. It was by this guy Mikolov and his collaborators, and they were all at Google. This was in 2013. Now, Mikolov's idea had actually been around for a long time. He'd been working on it for a long time, but no one cared. No one wanted to hear about it. Like, he couldn't get it accepted at linguistics conferences. And then all of a sudden, he got one through, and it changed everything. Absolutely everything. So in my mind, this is really heroic work, right? Now, the other thing that's really nice about it is it's actually really quite a sophisticated framework. From the point of view of machine learning, there's lots of really neat, elegant stuff in it. It's really nice, right? So something happens that wasn't possible before. We're able to get these really cool representations of words in the machine. And it's achieved through this really sophisticated, elegant framework, right? So the natural thing that we all thought, myself included, was that this is only possible through such sophistication. Like, you need this sophisticated approach in order to get these great results. People were like, theory, this was great. Machine learning theory, that is. So it was quite surprising when, a year later, this thing called GloVe came out. So GloVe achieves exactly the same level of results. But it's using a totally different approach. It's using an approach that is in no way elegant, and an approach that has been around for the last 35 years. Like, there's nothing... It's totally without the elegance and sophistication of Word to Vec. But that in itself is precisely the lesson, right? It's showing us that actually we didn't need all this sophisticated techniques to get to the end goal. All the information was already there. So it's also really, really useful work. Of course. Cool. All right. So I'm actually going to talk about these 2 things technically, but not too deeply. So Word to Vec is a rabbit hole you could talk about for 2 hours. That wouldn't be constructive, particularly given I've told you that all its sophistication is in fact unnecessary. Cool. So we've got these 2 techniques. What have they got in common? What they both have in common is they learn these representations of words from text. So you get a huge collection of text and you feed it into these machines, and out comes your word representation. So everything's learnt from the text. Right, and the other thing that is a bit hard to get your head around is the way you do this is you start with random representations of the words. So you just put the words anywhere in space. And then you read through the text, and then you update where you put these words in space such that words that have similar meaning are closer together. So the idea is you start off with total noise, everything's random, and you bring things into shape progressively by reading more and more text. Alright, so now let's look at word2vec. So this word2vec has all these sort of different approaches. We're only going to look at SIBO, that's fine. How does word2vec learn? Well, it reads text from left to right, as you might in English, and it looks at a small window. This is the word it's reading at the moment. So we've got once upon a time. Current word is time. And it looks at the words that surround it, say 2 to the left and 2 to the right. This is the context of that current word. So the current word is time, the context is upon a, in a. Then we're going to do something with that window, and then we're going to consider the next one. So after that, we'll consider the word, we'll just shift this window that way a little bit. The current word will move along one, and the context window will move along one as well. So we're sort of scanning over the text from left to right like that. But we kind of need to fix some names here. We've got the current word and we've got the context. Context just means surrounding words. Alright. So, what do? What we do is we forget the word we're currently reading. We pretend we don't know it. So if it's the word time, let's pretend it's not there. And we look at only the context words. So upon, a, in, a. And we try and guess from those context words what the current word was. So we pose ourselves a guessing problem, if you like. And from the point of view of machine learning, and this is the point where the page changes a little bit, this is a classification problem with multiple outputs. So the idea is you're looking at the context and you're trying to work out which of all possible words is the current word. And each possible word is a possible outcome, and you want to guess the correct outcome. And what we're going to do, so like the output of a classification problem like that is going to be a probability distribution over all the possible outcomes. So they're words, so here you've got the probability of the current word being cat, and trumpet, and time, and so on, for every word in your vocabulary. And what you want to do is update the positions of your words in space such that the outcome, like the prediction, is more like the truth. And the truth in this particular case is the current word is time. So you want the probability distribution that comes out of this machine to be like one hot. You want it to be all zeros for every word that's not the truth, and you want it to be one for the truth and zeros everywhere else. Alright, so how might you actually do this? Well, you could view a naive version of word2vec as a very simple neural network, where you do something called softmax classification. What do I want to tell you about this? So, here's the input. So the context is going in the top. We've got upon, a, in, a, and we're just counting the number of times each word occurs in that context. So you get like a word count vector, if you like. So we've got zeros, there's a 1 for a in, there's a 2 for a, and so on. So it's a really long vector. Then you apply a linear transformation down to a much smaller dimensional space, so it's a few hundred. And then you have another linear transformation back up to the high dimensional space, and then you do this softmax business, right? Which we'll get to a little bit later. Maybe the only important thing to take away from this is that the word vectors are actually the synaptic weights here. So if you like neural networks, these are the synaptic weights here. The word vector, like the point in space corresponding to a word, is exactly the strengths of all the synaptic weights emanating out from it in the top layer, which is what I put on the next slide here, but we're getting a bit technical. Alright, so that's how you could do it, but it's a bad idea, and it's not how word2vec does it. It's almost how it does it. So the problem with it is it's way too slow. So I told you the output is going to be probability distribution, right? Well, probability distributions have to sum with 1. So you've got to normalize the output so that this happens. You've got to Like you end up getting some output vector, then you have to divide through by its sum, so that the sum of the thing you divide, after you've done the division, is now 1. So you can consider it as a probability distribution. But to do that, you've got to sum all the possible outputs. And this normalization is really, really costly. What it means is that if you're just looking at it as a black box and you're looking at where the words are in space, it means when you move one word, you have to move all of them. You can't just move one in isolation of all the others. And this is really, really costly. And this is why this hadn't been done before. So Word2X innovation was really getting around this. And it offered a few different ways of doing it. The most impressive, I think, from a theoretical perspective, was this hierarchical softmax. And this other called negative sampling, which I suppose is more common. And anyway, these were the two innovations that I'm actually not going to tell you about. But they're the things that were really wonderful about Word2X. Well, they're kind of technical, and also, turns out, unnecessary. Wait, that's the next thing already. So, Word2X has this very elegant approach to getting around using softmax and training these word representations. And they fulfill all the promises I gave you in the beginning. Like, you really can do stuff with translation and things like that. Obviously it's statistical, so there's going to be error, but it's really pretty good. So what about Glove? Glove's the thing that was published the year after that uses technology that's really, really old. There's no sophistication in it at all. Works just as well. Well, first thing it does is it computes a co-occurrence matrix, if you like. So it looks how often each word occurs with every other word, and it just counts them up. Just forms this big table, if you like, matrix, where you've got one row for every word in your vocabulary. So you've got cat, potato, pet, next word, next word, next word. And then, similarly for the columns, you've got one word for every word in the vocabulary, cat, potato, pet, and so on and so on. And you put a number here that represents how often, say, pet occurs with cat, fairly often. How often it occurs with potato, not very often. And how often it occurs with pet. And you do this for all the words in the vocabulary. So you just read through your text and you see how often what occurs with what. The reason these aren't whole numbers here is because they sum together the inverse distance between two words. But whatever. The whole point is like words that occur in the same window together get their score accumulated. You're just counting how often things occur together in windows of text. Then what do? You take this logarithm, you ignore, when you do that, all the entries that are 0, and then you factorize it. So you've got this really big square matrix that is the logarithm of all these co-occurrence counts, and you find two skinny matrices, these two guys here, such that when you multiply them together, you approximately get this matrix back. And from a machine learning point of view, this is like bread and butter, old school, but it works super, super well. So this is what we're given, this is what we're measuring from the corpus, and this is the stuff we're learning through this process. The word vectors here are the rows and the columns of these two skinny matrices. So if you remember your matrix multiplication, the dimensions of this matrix and this matrix are going to match this dimension and this dimension respectively. So they're going to be indexed by the vocabulary. So if you wanted the word vector for cat, well, you've got one here and you've got one here. And they also learn some bias terms which they just throw away. Good. Well, that actually went remarkably quickly. That's what I want to tell you about Word2X and Glove.